A man falls asleep in his apartment at 11 p.m. The heating system in the wall has a cracked heat exchanger. He does not know this. The gas has been entering the room for 40 minutes before he closed his eyes. He will not smell it. He will not hear it. He will not feel it arrive. This is a second-by-second breakdown of what carbon monoxide actually does to a human body. The mechanism is documented. The outcome is determined entirely by one variable he cannot see. Let's start with what is already in the room. 1. The molecule. Carbon monoxide is a colorless, odorless gas produced by the incomplete combustion of fuel. A cracked heat exchanger, a running car in a closed garage, a blocked flue, any of these produces it in lethal quantities. The concentration in his room is currently 200 parts per million. At this level, a healthy adult will develop symptoms within 2 to 3 hours. He has been breathing it for 40 minutes. He does not feel any different. This is the central danger of carbon monoxide. The body has no receptor that detects it as a threat. There is no alarm system. The gas arrives and the body processes it without protest. By the time symptoms begin, the damage is already significant. 2. What is happening in his blood? Oxygen is carried through the bloodstream by hemoglobin, a protein in red blood cells that binds to oxygen in the lungs and releases it at the tissues. Carbon monoxide binds to hemoglobin at the same site as oxygen. It binds 240 times more readily. When carbon monoxide is present in the lungs, it outcompetes oxygen for available hemoglobin with almost no resistance. The resulting compound is called carboxyhemoglobin. It cannot carry oxygen. It cannot release oxygen. It is hemoglobin that has been functionally disabled. His carboxyhemoglobin level is currently at 15%. 15% of his red blood cells are no longer delivering oxygen to his tissues. His body has not registered this as an emergency yet. 3. The brain begins to notice. At 20% carboxy hemoglobin, the first symptoms appear. His head aches, not severely. A dull pressure behind the eyes that he would describe, if he were awake, as tension. His brain is the most oxygen-dependent organ in the body. It consumes 20% of the body's total oxygen supply, despite representing only 2% of its mass. A reduction in oxygen delivery is noticed here first. The neurons in his prefrontal cortex are beginning to fire less efficiently. His judgment, if tested right now, would be measurably impaired. His reaction time is slower. He would not notice either change. He shifts in his sleep. His body is attempting, without conscious direction, to find a position that optimizes breathing. It will not help. 4. The escalation. 40 minutes have passed since he fell asleep. His carboxyhemoglobin level has risen to 30%. At this level, his heart is working harder. The tissues are sending distress signals. They are not receiving adequate oxygen. The heart responds by increasing output, pumping faster to move more blood through the system in an attempt to compensate. This compensation has a ceiling. The blood moving faster is the same blood that cannot carry oxygen. Pumping disabled hemoglobin faster does not solve the problem. It delays the body's recognition that the problem cannot be solved this way. His breathing has deepened, another compensatory response. The respiratory system is detecting elevated carbon dioxide in the blood, a byproduct of cellular activity, and is increasing ventilation to clear it. More breaths means more carbon monoxide entering the lungs. The response is making things worse. 5. The cell-level damage. Carbon monoxide is not only displacing oxygen in the blood. At elevated concentrations, it is entering individual cells and binding to an enzyme called cytochrome C oxidase, a critical component of the mitochondrial energy production chain. Mitochondria are the structures inside every cell that convert oxygen into usable energy. Carbon monoxide disables the final step in that conversion. The cell receives oxygen, or what oxygen is still available, and cannot use it. This is called histotoxic hypoxia. The tissue is being starved of energy, not only because the blood cannot deliver oxygen, but because the cells cannot process the oxygen they do receive. His heart muscle cells are affected. His neurons are affected. His muscle cells are affected. Every system that depends on continuous energy production is simultaneously losing efficiency. 6. He cannot wake up. His carboxyhemoglobin level has reached 40%. He is no longer in normal sleep. His level of consciousness has dropped below the threshold where external stimulation would reliably wake him. His brain is in a state of metabolic suppression. The neurons are still firing, but at reduced capacity. The reticular activating system, The structure responsible for maintaining wakefulness is underperfused. It cannot bring him to consciousness. If someone entered the room now and shook him, he would not respond normally. He might groan. He would not wake. His body is showing one visible sign. His skin has taken on a faint pink tone, not pallor, not cyanosis, but an unusual flush. Carboxyhemoglobin is bright red. At high concentrations it gives the blood, and through it the skin, a color that has been described in forensic literature as cherry red. It looks like health. It is the opposite. 7. The heart under pressure. His heart rate is now above 110 beats per minute. The cardiac muscle itself is working under conditions of oxygen deprivation. Heart muscle cells have an exceptionally high metabolic demand and are among the first to show damage under sustained hypoxia. Small regions of the cardiac muscle are experiencing ischemia, insufficient blood flow to maintain normal function. This produces electrical instability in the heart's conduction system. He is at risk for arrhythmia, an irregular heart rhythm caused not by a structural problem but by the combined effect of hypoxia, elevated heart rate, and direct mitochondrial interference in the cardiac cells. Carbon monoxide poisoning kills through two primary mechanisms. Systemic oxygen deprivation is one, cardiac arrhythmia is the other. They can occur independently. In severe cases, they occur together. 8. The threshold. His carboxyhemoglobin level has reached 50%. Half of his hemoglobin is non-functional. His brain is receiving approximately half the oxygen it requires to operate. At this level, without intervention, the outcome is determined by time. Every minute that passes adds more carboxyhemoglobin, reduces oxygen delivery further, and increases the likelihood of cardiac arrest. He is not in pain. This is documented consistently in carbon monoxide cases. The progression from health to critical condition involves almost no subjective distress. The body is losing the capacity to generate the distress signals before it has registered the threat. The alarm on his phone goes off at 6 a.m. He does not move. 9. If the door opens now, fresh air enters the room. The carbon monoxide concentration begins to drop. His lungs are now breathing air with a normal oxygen to carbon monoxide ratio. Carbon monoxide dissociates from hemoglobin, but slowly. The half-life of carboxyhemoglobin in normal air is approximately 5 hours. This means that in 5 hours of breathing clean air, his carboxyhemoglobin level will drop by half. In a hospital, 100% oxygen is administered through a sealed mask. This reduces the half-life to approximately 60 to 90 minutes. The pressure of oxygen in the lungs outcompetes the carbon monoxide and accelerates its release from hemoglobin. In a hyperbaric chamber pressurized to 2 to 3 atmospheres with pure oxygen, the half-life drops to under 30 minutes. The increased partial pressure of oxygen forces carbon monoxide off hemoglobin and off cytochrome C oxidase simultaneously. This is the only intervention that addresses both mechanisms of damage at once. 10. What survives and what does not. His hemoglobin will recover fully within hours to days. The molecule itself is not permanently damaged. Once carbon monoxide dissociates, the hemoglobin returns to normal function. His neurons are a different matter. Brain cells that experience prolonged oxygen deprivation do not all recover. Some die during the hypoxic period. Others undergo delayed cell death in the days following exposure, a process called delayed neurological sequelae that can manifest weeks after the acute event. He may wake from this and appear largely normal. Then 2 to 4 weeks later, he may develop personality changes, memory impairment, difficulty concentrating, or movement disorders that were not present before. This delayed presentation occurs in an estimated 30% of serious carbon monoxide poisoning survivors. The brain appears to recover, then does not. The mechanism involves white matter damage and oxidative stress at the cellular level that continues after the carbon monoxide is gone. 11. The ones who do not open their eyes. Carbon monoxide is responsible for more accidental poisoning deaths than any other single substance in countries with widespread gas heating. Most occur during sleep. Most involve no pain, no warning, and no awareness on the part of the person dying. The forensic presentation is consistent. A body found in repose, no sign of struggle. Skin with that characteristic color. A room that appears entirely normal. The mechanism that makes it lethal is the same mechanism that makes it invisible. It competes silently for the same binding site as the molecule that keeps every cell in the body alive, and it wins that competition without any resistance from the system it is destroying. He was asleep when it started. The last thing his brain registered before consciousness left was a headache he assumed was from the day. The gas had been in the room for 40 minutes before he closed his eyes. It needed 40 more to finish.